All right, next I wanted to talk to you about the new topic, Chapter 9. This is shapes and geometries, I guess you might say. So we're going to be using two very similar terms. We're going to be talking about electron-domain geometries, and we're going to also talk about molecular geometries. Those are going to be two distinct things. But when we say the word shape, we're talking about molecular geometries. So those two things go together. Anyway, why are we going to investigate shape? Well, shape is very important for properties like boiling point or freezing point, properties like whether something dissolves or not. Those sorts of things often come down to the shape. And many other things, even reactivity comes down to shape often. So predicting shapes comes down to counting the spaces around the central atom that are occupied by electrons. Okay, so we've been looking at different spaces around the central atom. We haven't really been so much counting them, but that's going to be the really important part here, is being able to count those properly. Okay, we have a specific name for those spaces. We call them electron domains, hence that term I mentioned earlier, electron-domain geometry. Now, a domain is a space with electrons in it. It is not necessarily going to be inhabited by two electrons. It might be inhabited by one electron. It might be two electrons. It might be a double bond and therefore 4 electrons, even 6 electrons in a triple bond. So a domain does not necessarily mean like a set number of electrons. It just means a space. So if you look at this picture here, you've got 4 domains around the central atom. One of them is this double bond, right? And then each one of the single bonds counts as a domain, a space. And then the 2 dots down here, the lone pair, they also count as a domain, okay? So that would be a total of 4 domains. Now, that is going to determine a lot about how this thing is shaped, how this molecule is shaped. I know AB3 is not a thing, but it's a model for one. Okay. Now, the theory that allows us to predict the shape is going to be called valence shell electron pair repulsion theory. That's a mouthful. Most people kind of bastardize this name and call it VSEPR theory. That's not quite right. It's VSEPR, not VSPR, So it's not quite VSEPR, but close enough, right? VSEPR theory. So what it basically says is that electrons like to get away from one another, right? They like to minimize repulsion. So the best arrangement, according to VSEPR theory, geometrically for electron domains is the one that will get them as far away from each other as possible and therefore minimize repulsion. So that's why if you have 4 electron domains, like in the CCl4 compound, they don't just go in the 4 cardinal directions like you would expect if you just looked at the Lewis structure, right? Instead, they actually don't go 90 degrees from each other. They go 109.5 degrees from each other. And that's because you actually have 3 dimensions, right? You don't just have a flat piece of paper to put that compound on. You have 3 dimensions, and so they can find angles in those 3 dimensions that give them a little bit more space. Okay, so we get this interesting angle, 109.5 degrees. It's one we'll see quite a bit. Okay, now you can predict the electron domain geometry for all sorts of molecules. If there are 2 electron domains, in other words, 2 spaces around your central atom, that's going to be a very linear thing because the furthest 2 things can get away from each other, right, is 180 degrees from one another. And so we call that linear. If you have 3 electron domains, we call it trigonal planar because the furthest they can get away is 120 degrees from one another. 4 we already saw. The 109.5 degree bond angle situation that we had there, we call tetrahedral, like a tetrahedron, a 4-sided figure, right? If you go to 5, it gets really interesting. The angles actually cannot be all the same, weirdly enough, in 5 coordinate geometries. You can't get all the angles the same. Instead, what you get are some of them are 120 degrees from one another. Those are the ones that are sort of in the middle here. And we call those the equatorial positions for trigonal bipyramidal. And then you have the axial positions up and down. So the bond angles are either 90 degrees, or if they're on that equator, the equatorial positions, they're 120 degrees from one another. So that's a strange one. That's a really strange one. But, I'd challenge you to try and find a geometry that would be any better to get the angles any further away. It turns out to be impossible. So this is the best. If you have 6 different domains around the central atom, then you have 90-degree bond angles, and you get what we call an octahedral electron domain geometry. Okay, so those are the 5 electron domain geometries that we're going to deal with. We're not going to go beyond 6 because there just aren't many compounds that go beyond 6. Now, electron domain geometries are only part of the puzzle here. I mentioned that we have 2 different words that we use. We use electron domain geometries, and we also say molecular geometries. Now, a molecular geometry says that it describes only where the atoms actually are. What that means is it excludes lone pairs, right? So domains can be lone pairs, and those do affect the shape, but they're not considered part of the shape. That's kind of a weird thing. But like you can see in this ammonia compound, right, the electron domain geometry would have 4 positions, but the molecular geometry only has 3 things bound to that central atom. And so this space is empty, right? I mean, it has electrons, but you couldn't really see them, right? And so that's considered trigonal pyramidal for the molecular geometry, right? Because there's a triangle at the bottom, and it kind of comes up to a peak, so it becomes a pyramid. All right, so that's just an example. I'm going to show you more examples of this in just a bit, right? So molecular geometry, once again, is defined by the positions of the atoms. The lone pairs, the non-bonding pairs, do not get included in molecular geometries. Okay, I'm going to say you should all go to the handout. Now, this is linked on Canvas, and it has all of the electron domain geometries and molecular geometries. So here are all the electron domain geometries once again, right, on this sheet. And then here are all the molecular geometries that you'll need to know. Okay, so for the linear electron domain geometry, when there's 2 domains, if both of those contain bonds, then we call this linear. All right, so like carbon dioxide is a good example. If you go to the trigonal planar, where there's 3 domains, if all 3 are bonds, then the name of the molecular geometry is also called trigonal planar. But if 2 of them are bonds and 1 is a non-bonding pair, in other words, there's no atom up here, right? In that case, we call this a bent geometry, a bent shape, or molecular geometry. Okay, so an example of this would be like NO2 minus. Okay. If you go to 4 electron domains, and all 4 of them are bonding, then it's still called tetrahedral, right? Notice that the names don't change if all of them are bonding. But if 3 are bonding and 1's non-bonding, we already mentioned this name earlier, trigonal pyramidal, like ammonia. If you have 2 bonding and 2 non-bonding, we actually reuse a term we had earlier, right? We call it bent. So like water with 2 bonding and 2 non-bonding pairs is actually a bent structure. That's why it's polar. In fact, if water didn't have a bent structure, if it was linear, wouldn't be polar, wouldn't be able to do all the cool things it does. You can keep going to the 5-domain version, right, trigonal bipyramidal, and you notice you get some more variation in the shapes. You get a cool one called seesaw. It actually looks like a seesaw if you put it down on a table. It'll kind of go back and forth like a seesaw. You can get T-shaped, not too hard to figure out why that's called T-shaped, and then linear. Okay, and you might notice that the lone pair always goes on the equatorial positions in trigonal bipyramidal. There's a reason for that. We'll get into later, perhaps, but it always does. And then finally you have octahedral, and so octahedral has a couple of interesting shapes in it. If there's one lone pair, it's called square pyramidal, right? Because you have a square and then you have a peak, so square pyramid. And then if you have two lone pairs, they go as far away from each other as possible, so they end up at the top and the bottom right here, and so you get a square planar shape. Okay. So those are the different shapes that go along with the bonding. You can utilize this chart in order to do the worksheet. And here's a sort of a summary of the chart, right? A quick summary of the chart that shows you, if it's this many bonding pairs and this many non-bonding domains, then this is the shape you get or whatever, right? Okay. All right. So last thing that I wanted to show you is how to do the worksheet for today. So you're going to be given a compound, and you're going to be asked to write the Lewis structure, the dot structure, right? In the first column. The second column, you're going to put the electron domain geometry. The third column, the molecular geometry, and then the bond angles. And then I'll show you what I mean by structural diagram as well. Okay, so I'm going to do one. I'm just going to do CCl4. So CCl4, we all know by now, looks like so. Okay, and that's our Lewis structure. Now, if you look around the carbon in the center, the central atom, there are 4 electron domains, right, around that central atom, and therefore the electron domain geometry would be, if you said tetrahedral, you are correct. Okay, now because all 4 electron domains are inhabited by bonds, then we call the molecular geometry tetrahedral as well, right? If, let's say, 2 of them had been bonds and 2 had been non-bonding, then it would have been something else. It would have been bent in that case, right? Okay. Now, all tetrahedral structures have bond angles of approximately 109.5 degrees. Now, they actually do vary. They do, in fact, differ molecule to molecule, and if you have lone pairs, that actually does affect the bond angle slightly, but it's okay to just use 109.5 degrees for an approximate bond angle for these, and knowing that some of them will differ slightly. They'll differ slightly. They might be a little less, like 107 or 105 or something like that. Okay. Finally, we can draw the structural diagram. The structural diagram is just a way of showing sort of by perspective what's going on here, right? Our Lewis structure on the left there doesn't tell us anything about the 3D nature of this. And so I'm just going to real quick do the 3D nature of this. You have one bond that would be kind of coming out, and the way we show that is with a angled little wedge. And then you'd have one that is sort of going in, and you do that with kind of a like a dashed line. And then you have 2 of them that are in the same plane. Okay, so the ones that are in the same plane just get written with a regular line. The ones that are in and out of the plane of the paper, giving a little bit of 3D nature to this picture, are written with like a wedge coming out and with sort of the dashed line for one going into the paper. Okay, that's it. You should be able to do the rest. I would highly suggest utilizing the videos that I linked on Canvas to complete this. All right, see you next time.